Hello Year 12 and welcome to the second video here for Mathematical Induction. We were looking at series in the first video, and today we're going to look at divisibility by mathematical induction. These are less likely to involve a left-hand side and a right-hand side per se. What we're generally going to introduce with divisibility is some new variable which will be an integer. Now, if I can express, right, we're only dealing with integers here, if I can express some integer as, let's say, 7m, right, I've got an integer, right, let's say a is an integer, and m is an integer, and a equals 7m, then a is equal to 7 times m, which means that a is divisible by 7. So what we're going to do to prove these divisibilities is show that the expression is equal to, right, whatever that divisor needs to be, right, that multiplied by some fairly unspecified integer, variable. Let's jump in and see how this goes. So, as long as I add, subtract, multiply two integers together, I get another integer. Okay, different story if I divide. But if I have some expression that is some product difference of integers, that will be equal to an integer as well. That's important when we get to the end of these things, I suppose. So, prove by induction that this expression, 4 to the power of n minus 1, is divisible by 3 for all positive integers n. Okay? The first of our positive integers is 1. So we start by looking at the case n equals 1. Now, 4 to the power of 1 minus 1 is 4 minus 1 equals 3, which is clearly divisible by 3. So it's true when n equals 1. Now we assume that it's true for n equals k, and this looks like this. Now we say 4 to the power of k minus 1 equals 3m, where m is an integer. Right? 4 to the power of k minus 1 is divisible by 3, is what we're really saying. But it helps to make that an equation. Now we look at the case where n equals k plus 1. So we have 4 to the power of k plus 1 minus 1. And 4 to the power of k plus 1 we could say is the same as 4 to the power of k multiplied by 4 to the power of 1, so it's 4 times 4 to the k. Right, 4 times 4 to the k, minus 1 each. Now, if we think back to our previous result, 4 to the power of k minus 1 equals 3m. Rearranging that means that 4 to the power of k equals 3m plus 1. Now take that result here and replace the 4 to the power of k here. Means 4 to the power of k plus 1 minus 1 is equal to 4 times 3m plus 1 minus 1 is 12m plus 4 minus 1, or 12m plus 3. Now I factorise that, take a factor of 3 out, that's equal to 3 multiplied by 4m plus 1. Now 4m plus 1 is an integer, 4 times an integer plus 1. Right, is an integer. So I've got 3 times some integer. That means that 4 to the power of k plus 1 minus 1 is divisible by 3. Rightio? If I can take a factor of 3 out of that expression, and the quotient is an integer, right, then that expression is divisible by 3. So, now to our concluding statement. It's true for n equals 1. It's true for n equals k plus 1 if it's true for n equals k. Therefore, by the principle of mathematical induction, the statement is true for all integers. N is greater than or equal to 1. Okay, that's a divisibility example. Another one here. Reasonably tricky, this one I think. Works on our index laws a bit. Again, we look at, so all positive integers. The first of those is n equals 1. Now, if I tested this for n equals 3, for example, I suspect it'll be true if I substitute n equals 3. So if I start at n equals 3 and then look at n equals k and n equals k plus 1, I haven't proven it's true for all positive integers. I will have proven that it's true for all positive integers greater than or equal to 3. Right? I really have to lock in the first example. So n equals 1, 3 to the power of 3 plus 2 to the power of 3 is 27 plus 8 is 35, and 35 is 5 lots of 7. So that means that when n equals 1, my expression there is divisible by 5. True for n equals 1. Now let's have a look. N equals k, assume that it's true, which just means that 3 to the 3k plus 2 to the k plus 2 equals 5m, where m is some integer. I'm going to come back to that result before long. Now let's have a look. N equals k plus 1. So my expression here, I'm going to substitute k plus 1 in there for n. You get 3 to the k plus 3. Right, so it's 3n, and n is k plus 1, so 3 to the power of 3k plus 3. Now, k plus 1 plus 2 is k plus 3, so 2 to the power of k plus 3. I'm going to break this one up a little bit. Okay, 3 to the power of 3k plus 3 is equal to 3 to the power of 3 times 3 to the power of 3k. And here's 3 to the power of 3 times 3 to the power of 3k. I'm going to leave this bit be. Now, our previous result there, when n equals k, we found that 3 to the 3k plus 2 to the k plus 2 equals 5m. I want to substitute into that 3 to the 3k here. That's a bit of a nuisance to me. So, I'm going to make 3 to the 3k the subject of this equation. 3 to the 3k is 5m minus 2 to the k plus 2. Now I'll take this result and substitute it back in up here. So, my expression here is, right, let's come back a little bit there to see what happened. It's a bit of a leap there, I think. So, 3 to the power of 3 is 27. I'm going to have 27 times, instead of 3 to the 3k, I'm going to have 5m minus 2 to the k plus 2. Right, let's have a look. So there's the 27 times 5m minus 2 to the k plus 2 plus what was left there. So we've substituted, right, I've evaluated 3 to the 3 is 27, and I've replaced, right, that 3 to the 3k with 5m minus 2 to the k plus 2. Okay, from here, we're really trying to show that this is divisible by 5. It's looking a bit rough so far. 27 isn't divisible by 5. This term here doesn't particularly look to be divisible by 5, nor does this. So far, still a bit scrappy. What can we do? Well, I'm going to expand out a bit. 27 times 5m is 135m. Now, 27 times negative 2 to the k plus 2 plus 2 to the k plus 3. Now, 2 to the k plus 2 is 2 to the 1 times 2 to the k plus 3. 2 lots of 2 to the k plus 2. I have negative 27 of these, plus 2 of the same thing. That gives me, right, my 135m. This gives me minus 25 by 2 to the k plus 2. Now I can factorise, take a common factor of 5 out. And whatever's in the brackets here, that's still going to be an integer, right, because only multiplied, subtracted in there. So it's 5 times some integer, which means that it is divisible by 5. A certain amount of massaging there, but we got there. So n equals k plus 1 is divisible by 5, means the statement is true for n equals 1. It's true for n equals k plus 1 if it's true for n equals k, and therefore, by the principle of mathematical induction, the statement is true for all integers n is greater than or equal to 1. Righto. There was a bit of work there. Getting towards the end, I just want to have a look at a little bit of notation here. sigma notation we've seen before, where we add the terms of a series together. It might help, right, instead of using the sigma notation, to write it out as the sum of the terms for a while. Because often we just think about the nth term and not the sum of the first n terms. Here's an example. I want to prove that this is equal to this. Now this means the sum from the first term when n equals 1 all the way up to the nth term where n equals n. Right, so add the first term, then the second term, then the third term and so on. If I add all of those terms, I should get this. So this thing here, the left-hand side, right, my first term is 1 times 2 times 3. That's my first term. My second term, when n equals 2, 2 times 3 times 4. My third term, 3 times 4 times 5, and so on up until n times n plus 1 times n plus 2. Right, that's the left-hand side. Expanding it out there gives us a clearer picture. Now, if n equals 1, my left-hand side, right, I just want the first term, equals 6. My right-hand side will be 1 times 2 times 3 times 4 over 4 is 6, right, which is the left-hand side. So this statement is true for n equals 1. Now we assume it's true for n equals k. That means that first term, right, first term is 6. Second term, 2 times 3 times 4. Third term, 3 times 4 times 5. So on, up until k times k plus 1 times k plus 2. Remember, the sum of those k terms is equal to, substitute k to the right-hand side here. Now, let's look at the case of n equals k plus 1. My left-hand side is the sum of all these things. It's the first term, the second term, the third term, the kth term, and then the k plus 1th term. Yeah. That's what my left-hand side is. Now, the first k terms of that expression at the left-hand side can be written as, right, what was the right-hand side on the previous page, where n equals k. So my first k terms can be written this way, plus the last term, the k plus 1th term, which is this, k plus 1 times k plus 2 times k plus 3. That's my left-hand side. That's about as neat as I can get it for the time being, I think. I've put that up the top here a little bit. Hopefully we can see it. Looks like it might be just out of screen. It is a bit high. Anyway, so that's what we're working towards. We're going to try to make our right-hand side look like that. And in this case, I think it's best to work the right-hand side. So here's the right-hand side. K plus 1 times k plus 2, k plus 3, k plus 4. Okay, replacing n with the k plus 1. So my right-hand side looks like this, which is only a little bit like my left-hand side. The k plus 1, k plus 2, k plus 3, these three things over 4, that all looks good. There's k outside that I'm missing, and I've got and this 4 here is a bit of a nuisance, as well as these terms here. What I'm going to do is to take that last factor here of k plus 1 and distribute it amongst the rest of the expression. So I'm going to do k times this stuff plus 4 times this stuff. So k times these things plus 4 times the same things. Now the 4's cancel, and the first bit here is looking awfully like this. So that is k, that's at k plus 1, k plus 2, k plus 3, all over 4. That looks great. And then I cancel the 4's here, and I've got k plus 1, k plus 2, k plus 3, just as required. Okay, so now we have proven it's true, that it's true for n equals k plus 1 if it's true for n equals k. So a reminder there, why did we look at this question here? This wasn't a divisibility question. This was a question with sigma notation. It's really easy to make a mistake there and only look at the nth term, not the sum of all of the other terms coming before the nth term. Rightio. So write it out. Write a few of those terms out to begin with to make sure that you're on the right track. Rightio, I think that must be just about it. That's the end. If you've got any questions, make sure you see me in class.